Howdy. This video is on the ion-dipole and ion-ion interactions. The ion-dipole interactions, why ionic solids dissolve in water. The ion-ion interactions, why ionic solids form. After watching this video, you should be able to describe both of these interactions, identify when they occur, describe examples of them, and explain why the examples are important. So the ion-dipole interaction is an interaction between an ion and a polar molecule. Remember, whenever you see dipole, think polar molecule. So for example, when you dissolved a salt in water, you have ions surrounded by the water molecules, and so that gives you the ion-dipole interaction. Now, the larger the charge on the ion and the smaller the physical size, the stronger the ion-dipole interaction. And so here we have sodium in water. And so the sodium ion is a positive ion, and so it will be surrounded by the oxygen end of the water molecule. Remember, water is a very polar molecule. The oxygen is a partial negative charge. The hydrogen end has a partial positive charge.
Water molecules are made of hydrogen and oxygen. The hydrogen side of the molecule has a positive charge. The oxygen side is negative. When water molecules contact an ionic compound, such as potassium permanganate, their positive sides are attracted to the negative ions of the compound, and the negative sides of the H2O are attracted to the positive ions in the compound. These attractions allow the crystal lattice to break down, and the compound dissolves.
And so when an ionic solid dissolves in water, the ion-ion interaction is being partially overcome by the ion-dipole interaction, right? You're replacing the ion-ion interaction here with the ion-dipole interaction. Now, the ion-dipole interaction is pretty strong. For sodium and water, it's about 120. Now, sorry, there shouldn't be a line there. This is not a chemical bond forming, but you have the sodium and you have the water molecule, the oxygen end, and remember, the stronger the attraction, the lower the energy, the more stable, and so that's exactly what we're seeing here. That's kind of cool. If we flip the water molecule, so the partial positive side is facing the positive ion, we actually see the energy go up. Remember, the stronger the repulsion, the higher the energy, the less stable.
When a gas-phase sodium ion enters water, it becomes surrounded by water molecules, or hydrated. The ion-water connection results from ion-dipole forces indicated by a dotted line. It is difficult to determine the number of water molecules around a hydrated ion, but 6 is a good estimate for most cations.
And so when we have an ion from the gas phase go into the water, we have what's referred to as a hydration enthalpy. You're going from gaseous ions to aqueous ions. Now, often you don't include the water molecules listed here, and that's 6. I don't know what. So that 6 should be outside of the parentheses. That's a mistake in that video. This gives you a slightly different picture. And so the green one is, it's kind of hard to see. The green one is negative charge. So you notice that the hydrogen end of the water molecule is facing it. And the blue is positive charge. And so the negative end of the water molecule is facing it. And so for a single ion-dipole interaction, you could be looking at something on the order of 120 kilojoules per mole. And so we've assigned, when they're infinitely far apart, as being zero energy. As they get closer and closer, it's getting more stable, lower and lower energy. Remember, the lower the energy, the more stable. And so the distance between 0 to that minimum is about 120 kilojoules per mole. And so that's for sodium and the water molecule. Now that's one sodium and one water molecule. Hydration enthalpy is a measure of all the ion-dipole interactions that an ion experiences in water. And so you're dissolving the gaseous ion in the water. Hydration enthalpies are always negative. The larger the charge, the larger the hydration enthalpy. And the smaller the ion, the larger the hydration enthalpy. But please notice hydration enthalpies are larger than the strength of the ion-dipole interaction because they represent multiple interactions. So while one ion-dipole interaction is about 120 kilojoules per mole, the hydration enthalpy for the sodium ion is actually minus 444 kilojoules per mole. Now, the bigger the charges, the stronger the attraction. Again, it's just following Coulomb's law. And the smaller the radius, the stronger the interaction. And when you say bigger charge, remember it's the absolute charge. So you treat a +2 the same as you treat a -2. And so here we have Mg2 plus, and so it's got a hydration enthalpy of -2000, sodium -440, cesium -263. And so the difference here is that +2 is a bigger absolute charge. Now between the sodium and the cesium, you just have a difference in size. And so the smaller, the closer is stronger. And so that's why the sodium hydration enthalpy is -444, while the cesium is -263. But again, please remember, we're always talking about the absolute charge. So we treat a +1 and -1 the same, and a +2 and a -2 the same. Now, if we think about the hydration, you're going from a gaseous ion, and typically for gases, we assume intermolecular forces are negligible, to an aqueous ion. Now, aqueous just means that the ion is in water. So you're going from no intermolecular forces to ion-dipole attraction. The larger attraction, the lower the energy, the more stable. And so you go from something less stable to something more stable. And so that means energy will be released, which is why you have a negative hydration enthalpy. Enthalpy is actually how much heat is added to a reaction. And so if energy is released, the enthalpy will be negative. And so this negative energy is just due to the intermolecular forces, right? For the aqueous ion, you have ion-dipole. For the gaseous ion, you have no intermolecular forces. You assume intermolecular forces are negligible. And again, if you see a G, that stands for the gas phase. A Q stands for aqueous, and it means the ions are in water. And so for aqueous ionic solutions, the larger the absolute charge, the stronger electrostatic attraction between ions and water molecules, the more negative the enthalpy of hydration. The smaller the ions, the closer ions, the stronger the attraction, the more negative the enthalpy of hydration. And the absolute charge is the most important consideration. And so you could be asked to put the following in order of decreasing enthalpy of hydration. Remember, the stronger the attraction, the more negative the enthalpy of hydration. So decreasing enthalpy of hydration corresponds to increasing ion-dipole interaction. And so charge is the most important consideration. And so aluminum +3 should have the strongest interaction, the most negative enthalpy of hydration. The chloride and the lithium should have the smallest because it's the +1. And so based just on charge, this is what we have so far. Now the secondary consideration is size. So the smaller the closer, the stronger. And so lithium is smaller than chlorine. And magnesium is smaller than calcium. And so we get this as our final list. And so again, aluminum +3 is going to have the strongest ion-dipole interaction, most negative enthalpy of hydration. The chloride ion is going to have the weakest ion-dipole interaction and the least negative enthalpy of hydration. And if we look at a table of enthalpy of hydration, these ones in red are +1, and then here we have +2, a +3, and a -1. And so the +1s and -1s are typically a few hundred kilojoules per mole, except for hydrogen. And then the +2s are over 1,000, and the +3 is over 2,000. So again, charge is the most important consideration, and then size. And so the ion-ion interaction, is just the attraction between opposite charged ions. We think about it typically as 250 kilojoules per mole. That's just for a single ion-ion interaction. The last enthalpy is a measure of all of the ion-ion interactions. Now, for last enthalpy, it is the change in enthalpy when an ionic solid is converted to gaseous ions. And so for ionic solid, you have the ion-ion interactions. Gaseous ions, again, we assume intermolecular forces are negligible. And so the stronger the attraction, the lower the energy, the more stable. So you're going from something more stable to something less stable. And so you'd have to add heat. And so that's why last enthalpies are positive. If heat is added, that's a positive enthalpy. And so for ionic solids, the larger the absolute charge of the ions, the stronger electrostatic attraction, the larger the last enthalpy, the higher the melting point. The smaller the ions, the closer the ions, the stronger electrostatic attraction, larger last enthalpy, and the higher the melting point. And again, the most important consideration is the absolute charge. And so you could be asked to put ionic solids in order of increasing melting point. And so the first thing you do is you look at the charges. And so we see that sodium chloride is composed of +1, -1, lithium fluoride +1, -1, sodium oxide +1, -2, magnesium oxide +2, -2. And so that tells us immediately the magnesium oxide must have the highest melting point. Lithium fluoride and sodium chloride have the lowest. And so based on charges, we get that. And now, if we want to distinguish between sodium chloride and lithium fluoride, lithium is above the sodium on the periodic table. Fluorine is above chlorine. And so lithium fluoride is composed of smaller ions. And so the sodium chloride should have the lowest melting point. And so for last enthalpy, again, charge is the most important consideration, and then size. And last enthalpy and melting point go together pretty much. Typically, the lower the last enthalpy, the lower the melting point. The higher the last enthalpy, the higher the melting point. I should also again remind you that last enthalpy is a measure of the strength of the ion-ion interaction. And so for both the ion-ion interaction and the ion-dipole interaction, the absolute charge is the most important consideration. The larger the charges, the stronger the attraction. And for both of them, the smaller the ions, the closer the ions, the stronger the attraction. And again, this is just because they follow Coulomb's law. And so the stronger the ion-ion interaction, the higher the melting point, larger the last enthalpy. The stronger the ion-dipole interaction, the more negative the enthalpy of hydration. I hope that was helpful.